You're good. Hit the record.
Okay. Hi, my name is Naomi Park. I'm from Greenwich High School, and I just want to say thank you so much to CTJSHS for giving me this opportunity to present and share my research. And my research is entitled Concurrent Removal of Rising Soluble Ocean Carbon Dioxide and Oil and Water Contaminants via Multifunctional Remediation Framework. So, just to give you some insight into what my project is about, today there are three pollutants that are detrimentally harming our planet with limited ways on how to solve them. One is carbon dioxide. The atmospheric concentration of CO2 is increasing at an unprecedented rate. The oceans presently absorb nearly a third of all CO2 emissions, and by the end of the century, they could be nearly 150% more acidic. Two, oil spills. 1.3 million gallons of toxic crude oil are released into the oceans every year, and traditional methods of remediation only remove the visible surface contamination. This leaves behind this invisible oil that is equally as harmful but harder to remove. Three is plastic pollution, in particular styrofoam. Polystyrene, the primary component of styrofoam, is one of the hardest materials to recycle, leaving our planet drowning in a sea of waste that can take hundreds of years to degrade. So, hypercross-linked polymers, or they're known as HCPs, represent these class of nanoporous materials which have gained recent attention to be used as environmental sorbents to capture and remove pollutants. However, traditional HCP synthesis involves using costly reagents, but recent literature by Dong et al. Demonstrates the development of a cost-effective method using styrofoam waste. Now, this kind of leads me into my engineering goal, which aims to develop a cost-effective and environmentally safe remediation method via development of a multifunctional remediation framework, what I call as MFRF, via application of styrofoam HCPs to effectively remediate crude soluble oil and carbon dioxide while concurrently lowering the ecological footprint of styrofoam waste. So, to detect the oil and water contaminants, I used fluorescence spectroscopy throughout the entirety of this research. And I used mobile 89 octane as my oil contaminant. But it's really a mixture of a lot of aromatic hydrocarbons that all have their own fluorescent signatures. So, what I did was I was able to isolate the signature of benzene, a component of gasoline, and basically report remediation of the oil contaminant through remediation of benzene. I found that the peak excitation was at 255 nanometers with an emission of 278 nanometers. The x-axis on this graph represents the wavelength in nanometers, and the y-axis represents fluorescence intensity. Then, to quantitate the oil and water using this technique, I created serial dilutions of the maximum solubility of benzene. This was found at 1.7 grams per liter and collected their emission spectra. For my calibration plot, the x-axis represents benzene concentration and the y-axis represents fluorescence intensity. Now, to actually synthesize the hypercross-linked polymers, I refluxed and stirred the materials listed on the screen, including styrofoam, for 12 hours. The crude product was then washed, yielding a brown powdery product. The HCPs were then analyzed via ATR-FTR spectroscopy, and then for all IR spectra reported in this research, the x-axis represents wave number and the y represents percent transmittance. So comparison to the IR spectrum provided in the paper, it highlights its successful fabrication. And then I also took an SEM image, as you can see on your right, to see what my created product looks like. So the first thing that I wanted to do was test the efficacy of the pure HCPs in each respective contaminant before delving deeper into practical implementation methods. And to do this, I made six 12-milliliter bottles of just the contaminated seawater to act as the control for volatile outgassing, and then six with 25 milligrams of the HCP. Each bottle represented a time point. I had 30 minutes, an hour, 2, 4, 12, and 24 hours, and they were each discarded after use to account for volatile outgassing once again. Regarding soluble oil remediation, in the first 30 minutes of water treatment, more than half of the oil contaminant was removed, with up to 88% remediation in 24 hours. This corresponds to roughly 1.5 grams of oil. As for CO2, here's the mechanism of what's kind of happening when CO2 gas is absorbed from the atmosphere. For every mole of CO2 absorbed from the air in reaction 1, there is one hydronium ion released into the ocean. So I was able to measure remediation of CO2 indirectly as a function of H+. CO2 remediation was then quantified via a relative increase in pH, and the pH increased from 4.5 to 6.4 over 24 hours, indicating 95% remediation. The proposed design of the multifunctional remediation framework, known as MFRF, includes a melamine sponge to act as the base, a 15% PTFE dispersion to act as the binding agent, and then the HCPs that I previously synthesized for pollutant removal and capture. So I took FTIR spectra and SEM image of the sponge at each step of its construction. As you can see, in the PTFE-coated sponge IR spectrum, the sponge is fully coated with the PTFE, leaving no traces of melamine. Then I took an FTIR and SEM of the completed HCP sponge. The circles on the IR highlight HCP application throughout the entirety of the device. Regarding application of the MFRF, the framework, it includes this floatable framework so the device can be implemented atop ocean water. The completed device can be implemented either at the shoreline via tethering or at deep sea depths using a buoy. Additionally, I envision that an eco-friendly enclosure will be built around the device to prevent disruption and consumption. Now, to actually test my framework, I really wanted to do everything I could to create an airtight system. So I bought these acrylic boxes and drilled 6 holes of 12mm diameter into the wooden top. Then the HCP sponges I previously made were inserted into tubing of the same diameter. Occupying the 6 holes created were 3 of my HCP sponges, 2 rubber stoppers, and then a sampling port so I had access to the solution without volatile outgassing. The framework is then inserted onto the box, and the entire top was parafilmed, again to make sure I didn't lose any gasoline or CO2 into the air. So first, I wanted to do independent remediation experiments of the created device for each contaminant separately before trying to concurrently remove them. I used contaminated seawater of soluble oil first, and these experiments were carried out with the created HCP sponges, just PTFE coating sponges, plain melamine sponges, and no treatment at all to act as controls. At specific time intervals, the solution was drawn out using a needle syringe from the drawing port, analyzed, and then reintroduced into the testing vise to limit the amount of headspace present. Analyses were performed at 6 time points up to 24 hours, and this process was repeated for the trials with the just contaminated CO2 seawater. As expected, for the controls, there were no or roughly 5% remediation of the soluble oil. However, the HCP sponge resulted in significant remediation with a removal efficiency of approximately 92% of the contaminant. In terms of CO2, the MFRF remediated roughly 95% of the contaminant, again found through a relative increase in pH. And so now the development of a device to simultaneously remove multiple contaminants is an area of research that has not been thoroughly explored. And to address this gap, I conducted experiments to assess the effectiveness of the framework in remediating both soluble oil and CO2 under realistic conditions. So current methods of oil remediation include oil booms. That's the most popular. And once an oil boom removes the visible surface contamination, the maximum solubility of oil is left behind. However, the concentration of CO2 is not nearly as high as presented in previous trials. The oceanic CO2 concentration has increased around 100 ppm since the Industrial Revolution. This equates to around a 0.1 pH decrease. And throughout these trials, I found that it only took 12.6 minutes for this device to reach a suitable oceanic pH of 8.2, with 92% of the oil contaminant removed. Now, with all of this in mind, I wanted to try and push the device to its limit and get a real idea of its capacity in a shorter amount of time. So this was like step 2. Given that it was successful in removing both contaminants prior at realistic concentrations. What I found was that even when the H plus concentration increased by 100 times, it was successful in removing 85% of it, as well as 1.2 grams of the oil contaminant. These trials really highlight that as well as having duality of function, even when you crank up these concentration, the device works well too. After there was verification of remediation, I wanted to conduct a reuse study. There's 2 parts to this study, and the first step is testing the recyclability of the HCPs itself, the powder that I made. So post-oil remediation trial, the HCP was taken out, placed atop an FTR spectrometer, and its spectrum was taken. Then I let it dry on the spectrometer and took the IR of the dried HCP. FTIR analyses highlight that following the removal of crude soluble oil, the spectrum of the dried HCPs closely resembled that of the new ones. This demonstrates that the HCPs were not significantly altered or degraded by the remediation process and therefore viable for use. And the second part of this study, was to test the reuse of the actual device created. So what I did is I took a used HCP sponge, transferred it to a bottle, and heated it at 30 degrees. Some of this headspace was then drawn out and then injected into an IR gas cell. This process was repeated with the controls, the melamine sponge, and the PTFE-coated sponge. FTIR analyses of this headspace highlight that only gasoline was detected in the HCP sponge, suggesting that none of the other components of the HCP sponge were lost or degraded by the remediation process. Additionally, given that no gasoline was detected in the headspace of the controls, it can be inferred that the gasoline was selectively absorbed to the HCPs within the HCP sponge, providing further evidence of its efficacy in remediating crude soluble oil. Finally, I decided to conduct alternate longevity trials, which basically included cyclical use of the device. These trials highlight the device's capacity. Regarding oil, it took 6 days for the sponge to reach its capacity around 6 grams of oil, and in CO2, it took 3 days to reach capacity of 3,700 ppm. With all this data that I got throughout this research, I wanted to investigate what the device could really do in a larger body of water. Therefore, based on capacity and realistic concurrent trials, I calculated that in 36 hours, 3 of the HCP sponges I made, or 1 framework, would be able to increase the pH of ocean water by 0.1 in around 28.6 kiloliters of water. This is a little less than half of the volume of your regular backyard pool. Additionally, in this instance, if you were to clean the amount of a full pool by using 2 of these frameworks, it would stop 7 grams of styrofoam ending up in a landfill. Additionally, regarding possible implementation, as I've mentioned before, oil blooms only remove visible surface contamination. The oil on top is constantly depositing toxic soluble oil into the surrounding water. Therefore, I envision my sponge lined and attached around the boom to basically capture the soluble oil before it disperses and contaminates the surrounding water. And this, what I'm showing you right here, represents a really aggressive situation, which was modeled in my experiments by using the maximum solubility of benzene. So what I envision is you could leave these sponges in contaminated water for around 5 days to reach capacity. Additionally, they could also be implemented in a less aggressive scenario where they could be left for more days or even weeks. To summarize, the HCPs alone exhibited remediation capability. However, the constructed framework exhibited greater remediation efficiency. The MFRF is stable and safe for marine life with a multitude of implementation possibilities. And furthermore, this device has an elegant implementation because it takes little effort, as all you have to do is simply leave the framework in contaminated water, wait till it reaches capacity, and take it out for reuse, recycling, and removal. A tested framework costs only $9. Okay.
Yep. Thanks, Naomi. We
Thank you.
appreciated your presentation. We now just go out to the judge.